Welcome to solverfy.
We'll be looking at more problems on friction. Consider the diagram shown in the board. We want to determine the magnitude of this force P going that direction and consider the such that the polar rotates in a clockwise direction. Now, to solve this problem, we need to understand the situation here that the collar slips on the shaft. So, slip is involved, and we need to determine what we call the friction circle radius, as well as apply equilibrium and solve every resulting equation, yeah, to get an answer. The friction radius, circle radius is equals to the radius of the shaft times the sine of kinetic friction, angle of kinetic friction, pi subscript k. But we don't know this because it's not giving the question, but we can figure it out by applying this relation. The arctan of mu k is given in the question, which is the coefficient of kinetic friction. When we solve that, when we plug it in, we are going to arrive at this angle to be 16.7 degrees. Okay. Now we can plug this value as well as the radius of the shaft, which is given as 2 inch. Plug it into this equation, we are going to arrive at 0.58 inch. Okay, as the friction radius, circle radius. Now we cannot apply equilibrium to solve the problem, but this arrow, this reactive force that is here, we don't know it. So we can apply something that look like this. We know that if we have from Pythagoras theorem, we have arrow as a resultant force, the components or arrow is equal to the its component, the sum of the square of its uh, components, the root of the sum of the square of its component, something like this, Rx. So with this in mind, we can forge ahead because we now know what the components look like. Okay, solve this. So we cannot consider equilibrium in the vertical direction. If we do that, we are going to have the forces that are acting there to be, we have minus 20, sorry, 20 IB in that direction. So it's minus 20 plus the force, the horizontal component of this force equal to 0. When you solve this, you're going to arrive at your horizontal component to be equal to 20 IB. Okay. Now, we can also apply equilibrium in the horizontal direction. When we do that, we're going to have it's equal to 0, such that we are going to have uh, the P going in that direction to the right minus arrow subscript x is equals to 0. When we solve this, we are going to arrive at the value of this one. Okay, this one to be equal to P. Okay, we can come back to that relation that I dropped, that arrow, put them into this equation. This you will have something like this, P for the horizontal component and 20, which you already know, for the vertical component. Just put their square there. You can now take moment about O. Take moment about O. Let's okay in the diagram. Let's see whether there's O there. Yes. So about that point in the diagram, you take summation of moment about O. You're going to arrive at equal to minus P times the radius of the collar plus 20, that 20 force The radius of the collar is also the perpendicular distance plus uh, this force p squared plus 20 squared, and this one will go through the perpendicular distance of actually the RF which we have found. So everything will be equal to 0. So you can solve this one. When you solve it, you're going to arrive at P. You're going to arrive at an equation 14.25p squared minus 612. Okay, point 3. This one is not clear enough. Look, 612.3p. Okay, 612.3p plus 5730.89 equal to 0. So this is a quadratic function. So when you solve this, remember you arrive at where we have plus or minus, you take the positive, because we are considering that the collar rotates, we rotate in a clockwise direction. Okay, so if we take that, our answer, we are going to have arrived at our answer to be, sorry, we arrive at our answer to be P is equal to 29.2 29.2 IB. So this is the answer when it rotates, the collar rotates in the clock.